For 20 consecutive years, IBM inventors have generated more U.S. patents than those of any other company. While this patent milestone is important, what the numbers really demonstrate is the outcome of IBM's unwavering commitment to exploration and fundamental research and development.
20 years of patent leadership per se, just the raw number, is actually not the point here. It's an indicator. When you involve that, when you take that and you mix it in with the impact of those innovations, of those inventions, that's dramatic.
IBM's institutional patience allows scientific discoveries to find their way into the market, contributing to the creation of new industries or industry segments, and the economic growth associated with it.
Patent leadership means we've done this for a long time. The investment to let people be creative when we're not always sure what the business outcome is really going to be.
For example, when IBM researchers made a discovery about laser ablation, they could not have predicted that it would lead to LASIK eye surgery, or that new advances in semiconductor technology would enable the cell phone industry as we know it today, or that its research into machine language would be a key component of the Watson system that is now in the process of transforming healthcare and other industries.
I think it's amazing actually that a single company can hold that leadership role for 20 years, and when you look at the numbers, over 6,000 patents in 2012 is just amazing.
IBM's chairman and CEO, Ginni Rometty, has called the coming times a new era in computing, a new era in cognitive computing, a new era in cognitive systems. The phrase new era signifies not an incremental or a tactical shift. It signifies a fundamental strategic and technological shift in terms of the technology and what we do with it.
If one of the ideas is to get computers to interact with us the way we want to interact with one another, instead of us sitting down and programming a computer someplace, then this notion of computers that deal with images the way we do, or being able to visualize what we do in a way that isn't a spreadsheet, it isn't a bar chart, it's really visual, it's really the way humans interact with the world. I think that will transform how we do a lot of what we do in the business world as well as in our private lives.
I mean, the computers we've been using for the past 60 years have been amazing machines, but they've all been slaves to what's called the von Neumann architecture, a certain way of constructing a computer that involves separating memory and processing, doing things in a sequential step-by-step fashion, and doing those things according to a program that's been pre-written. So our brains don't work that way at all. They do things in parallel. Memory and processing are very intimately intertwined, and there's no program. We do the things we do because of the way our brains are configured. So it's been very difficult for computer scientists to try to simulate the brain using traditional computers, and that's why we're working on this project where we're trying to invent an entirely new computer architecture that works more like the way our brains do, and hopefully we'll be good at the same kinds of tasks that our brains are good at.
The essence of cognitive computing, to me, is to think about the difference between the way that most computers work now and the way that the most sophisticated computers on the planet work, and those computers are the things that we all carry around in our heads, along with, you know, mammals and all the other little animals that run around and do these amazing feats in real time, taking in their environment, understanding, making decisions very fluidly, you know, and responding. And how often have you looked at a computer while its little hourglass is spinning and then it does the wrong thing, right? So the ability to bring a level of fluidity and appropriateness to the way that we interact with computing, making computers actually more like biological systems, whether or not they're brains, but having that kind of fluidity where they respond and react appropriately. So you feel like you're dealing with another living thing, not a machine.
When you look at what the human brain can do, it's really amazing the way we can reason about things and think very deeply about things. But where we start to run into a wall is when we're faced with leveraging huge volumes of data. So looking through tons of documents, millions of books, for instance, is almost impossible for the human brain. But in order to push the boundaries of human cognition, we want to provide access to all of that data. So I think one of the first challenges or tasks of these cognitive computing systems is to facilitate or enable human cognition beyond these barriers. And that's exactly what Watson is all about, in fact. It's about providing access to huge volumes of literature, unstructured information, text, digesting it, evaluating it, and providing efficient access for humans to that information to help that human cognitive process.
Cognitive computing is about drawing inspiration from the brain and yet respecting the technological and engineering constraints of the society to create a new generation of computers and a new generation of services and solutions to make the world better.
And you get this whole ecosystem of innovation going because you never know where a particular patent is going to lead.
There are some great examples of things that when we started them, we had no idea what was really going to happen.
Serendipity plays a large role in research. And so a lot of times you create something that had an intended purpose, but it didn't necessarily work out that way.
When I first interviewed at IBM, I didn't know that IBM was even working in nanomedicine. I was presenting a poster at a conference just a few months before I finished my PhD, and one of the scientists here came up to me and said, "How would you feel about continuing working in nanomedicine at IBM?" And I was like, well, what's going on? IBM is a computer company. Why would they be working in nanomedicine? Well, it turns out many of the materials used in the semiconductor industry actually apply very well to materials that are used in medicine.
I think one interesting story on this notion of working on something and then much later you discover what it's really good for is an area around fine-grained weather forecasting, something we internally call deep thunder. And we have a group of researchers that have been working on this for probably 15 years. They're meteorologists, and it's not about is it going to rain, it's what happens on the ground when it does. It's is it going to flood in Rio? It's can you predict the power outages from the next storm before it happens so you're ready? Can you predict what the wind farm will produce tomorrow so you know how to balance the grid in advance? It's everywhere, but when we first started, it was absolutely a scientific curiosity.
That's the beauty of it. You don't know what your invention is going to be used for, decades from now. It solves a particular problem that you thought of, but what makes it patentable is that it's applicable to a larger sphere than what you invented it for. That gives you that little kick that you're pushing the boundaries of computer science. That's amazing.
I think one of the important things to remember is that invention and innovation take a long time. And when you begin the process, you have one idea about what you're trying to accomplish. By the time you're finished, you may have a very different idea.